In exactly 7 months, a machine the size of a school bus will do something that defies the laws of common sense. This is why BepiColombo is about to change everything we know about Mercury. Right now, billions of kilometers from home, a $2 billion gamble is screaming toward the sun, fighting a gravitational pull so violent that it is actually harder to reach Mercury than it is to leave our solar system entirely. We have only been there twice before. Both times, we came back with answers that broke our textbooks. But this time is different. We are not just sending a camera, we are sending the first ever X-ray eyes to another world. We are going to see things no human has ever seen, from hidden diamond layers to ice that should not exist. But there is a problem. A silent glitch in 2024 almost killed the mission, and a massive solar flare just scrambled its brain. With the clock ticking down to November 2026, the question is not just what we will find, but will the spacecraft survive long enough to tell us? Gravity, at Mercury's doorstep, is not a gentle invitation, it's a trap. Reaching the innermost planet is not a matter of aim and fire, it is a battle against the sun itself. The closer a spacecraft falls toward that searing furnace, the faster it is dragged along, gaining speed that must be bled away, not added. For BepiColombo, the energy cost, the so-called delta phi, defies every instinct. Escaping the solar system takes less effort than dropping inward to Mercury. The numbers are unforgiving. To break from Earth's orbit to Mercury's, a direct shot would demand more propellant than any rocket could ever carry. This is the paradox that stumped generations of mission designers. The deeper you go into the sun's gravity well, the steeper the climb to slow down. It is like trying to stop a freight train by throwing out anchors while barreling downhill. The only way to survive is to borrow the momentum of other worlds. That is where the insight of Giuseppe Colombo comes in, a quiet mathematician from Padua who, in 1965, saw a way out. His idea was simple: use a chain of planetary flybys, not to speed up, but to slam on the brakes. By swinging behind Venus, then Mercury itself, a spacecraft could siphon off just enough energy to spiral inward, step by step, without running out of fuel. Colombo's vision was more than clever math. It was a blueprint for the impossible. Today, BepiColombo is the living proof. A 3-part stack riding a carefully plotted path. Each flyby shaving off speed, each maneuver a calculated risk. The mission's trajectory is not a straight shot. It is a cosmic dance, choreographed to cheat the sun's grip. Every kilometer traveled, every gravity assist is a gamble with the laws of motion. And at the heart of it all is a simple, brutal truth. To reach the forbidden planet, you must first learn how to fall, and then how to stop. Every number behind BepiColombo is a measure of risk, ambition, and humanity's hunger for answers. The mission launched on October 20th, 2018, riding an Ariane 5 from French Guiana, a liftoff that marked the start of an 8-year odyssey, not just across space, but against the odds. The price tag stands at roughly $2 billion, a sum that underscores just how much is at stake for Europe, Japan, and planetary science itself. This is not just another probe, it is the most expensive, complex effort ever mounted to reach the innermost planet. The journey covers nearly 7.9 billion kilometers, more than 50 times the distance from Earth to the Sun. That path is anything but straight. BepiColombo's route demands 9 planetary assists, a single slingshot around Earth, 2 dives past Venus, and 6 perilous encounters with Mercury itself. Each flyby is a calculated maneuver to siphon away speed, using gravity as a brake instead of a boost. Without these assists, the spacecraft would be doomed to overshoot, flung out by the sun's relentless pull. Packed into the spacecraft are 16 scientific instruments, divided between 2 orbiters. The Mercury Planetary Orbiter carries 8 tools for mapping, chemistry, and topography. MEO, the Mercury Magnetospheric Orbiter, brings 8 more, designed to probe Mercury's magnetic field and plasma environment. Both orbiters travel together, shielded and propelled by the Mercury Transfer Module, until the moment of separation at the edge of Mercury's gravity well. All calculations point to November 2026 as the decisive date. That is when BepiColombo will attempt orbit insertion, a single chance to break, capture, and survive. If the timing is off, if the numbers slip, the mission's $2 billion gamble could end in silence. The facts are cold, but the stakes are anything but abstract. This is the price of trying to unlock the secrets of the forbidden planet. Alarm sounded in the control room at 0214 UTC. The telemetry stream from BepiColombo's transfer module showed a sharp drop in xenon pressure, plunging from steady to critical in less than a second. On the ground, Dr. Marina Kohler and her team at ESOC watched the thrust values collapse. Discharge current on all 4 Hall effect thrusters fell by more than half. In orbit, BepiColombo's autopilot triggered an emergency shutdown. The spacecraft began to drift, riding momentum alone, while the sun's gravity waited to claim its prize. Within minutes, engineers traced the failure to a microfracture in the main xenon feed valve. The risk was existential, with the primary line compromised, the mission's propellant margin, already razor-thin, in danger. Every meter per second of lost velocity could mean missing Mercury entirely, dooming the $2 billion gamble to a silent flyby. There was no time for deliberation. Kohler, JAXA propulsion chief, Takeshi Yamamoto, and the Mission Assurance Board convened by a secure line. The weak capture contingency was authorized. The plan was surgical. First, the system switched to the secondary xenon line, reducing thrust to 45% of nominal to prevent further stress. Then, over the next 48 hours, the remaining thrusters executed a sequence of 4 low-thrust burns, a spiral arc designed to bleed off just enough energy for Mercury to catch the spacecraft in its gravitational net. The change in velocity penalty for this maneuver was 12 meters per second. On paper, it was within the mission's margin. In practice, it was a roll of the dice against the laws of celestial mechanics. Each burn was monitored in real time, every data packet scrutinized for signs of further leak or attitude drift. Engineers calculated the propellant cost to the gram, aware that a single miscalculation could push BepiColombo past the point of no return. When the final burn concluded, the trajectory was restored barely. The spacecraft was now set to enter a high elliptical capture orbit at Mercury, with just enough fuel left for the critical descent. The crisis had exposed the fragility of the entire mission: one fractured valve, a 48-hour window, and the fate of decades of planning hanging on the outcome. The sun does not rest, and for spacecraft daring to approach Mercury, its violence is never far away. On May 4th, 2024, just weeks after BepiColombo's propulsion scare, the mission faced a new threat. An X-class solar flare erupted from active region AR3110. The flare unleashed a torrent of high-energy protons, and within hours, the spacecraft's radiation monitors registered a spike in proton flux. Levels echoed in the GOES satellite data streaming back to Earth. Inside BepiColombo's electronics, the storm's fingerprints appeared as chaos in the memory banks. The Mercury Planetary Orbiter's solid-state recorder, a 2-terabyte flash array, began reporting corrupted telemetry packets. Engineers at ESOC traced the problem to hundreds of bit flips, tiny digital errors caused when energetic particles punch through memory cells, flipping ones to zeros and zeros to ones. At the same time, MEO's power distribution unit experienced a sudden surge, forcing an automatic reset of its entire instrument suite. For a moment, the spacecraft's scientific eyes went dark. In the control room, Dr. Sofia Mendoza and her systems team moved quickly. They cross-checked housekeeping telemetry against the radiation monitor, confirming that the errors matched the timing of the solar event. The next steps were drilled into every engineer. Initiate a full error correcting code scrub of the affected memory, re-upload the critical firmware tables, and command both orbiters into safe mode. The error-correcting routines worked as intended, rewriting corrupted sectors from redundant backups. Within minutes, MEO's instruments rebooted, and the Mercury Planetary Orbiter's data stream returned to normal. No science was lost, but the message was clear. At 0.3 astronomical units, the solar wind is not a breeze, but a barrage. Every X-ray burst or proton storm is a roll of the dice for the mission's survival. The error correction systems had done their job this time, but the margin for error is razor thin. Each new solar event brings another test, another reminder that the forbidden planet is guarded by more than gravity. For BepiColombo, the journey is a battle not just against physics, but against the sun's relentless assault on silicon, memory, and time. BepiColombo's cruise phase has already delivered a string of scientific wins, each one a testament to the instrument team's persistence. Mio's magnetometer picked up a chorus chirp, a low-frequency ripple in the plasma, the signature of electron cyclotron mass emission. This chorus, familiar from Earth's own magnetic storms, now echoed through Mercury's environment, revealing a space weather system far more active than once believed. For plasma physicists, it was the first sign that Mercury's magnetic field is anything but dormant. During a close flyby, the Mercury Planetary Orbiter's camera captured the first resolved image of Stoddart crater. Terraced walls and a central peak stood out in sharp relief, shaped by impacts at temperatures that can melt lead. No previous mission had revealed such detail, and the battered surface of Mercury began to give up its history, one crater at a time. The MERTIS spectrometer then measured Mercury's dayside at a blistering 420 degrees Celsius, hot enough to vaporize zinc. These numbers confirmed that BepiColombo's thermal shielding and sensor calibration were holding, even as the spacecraft faced relentless solar wind. Meanwhile, the MIX-S X-ray spectrometer completed its final cruise phase checks. Its detectors, cooled and tuned, achieved a signal-to-noise ratio of 20, promising to reveal the fingerprints of iron, silicon, and magnesium across Mercury's crust. Each data packet is a quiet victory, proof that the mission's science payload is not just enduring, but thriving. Yet with every answer, Mercury offers up new mysteries, urging the teams onward. BepiColombo's X-ray vision has been switched on. Deep inside the Mercury Planetary Orbiter, the Mercury Imaging X-ray Spectrometer, MXS, has finished its calibration, marking a turning point in planetary science. For the first time, an entire planet will be mapped in X-rays, not just sampled in isolated spots. MIX-S is more than a camera. It's a forensic tool designed to uncover Mercury's secrets hidden beneath layers of iron, silicon, and potassium. The science is straightforward and powerful. When solar X-rays hit Mercury's surface, atoms there emit their own X-rays, a process called fluorescence. Each element, iron, silicon, and potassium, releases photons at specific energies. MIX-S detects these unique fingerprints, measuring their abundance with a signal-to-noise ratio between 15 and 20. This level of precision means scientists can now see not just what elements are present, but how much and exactly where they are found across Mercury's battered crust. Professor Laura Basile, a lead MIX-S scientist, recalls the first calibration spectra. She said, "We saw the iron and silicon lines clear as day, and even the faint potassium peak. It was the proof we had been waiting for. Mix was ready." These measurements matter. Theories about Mercury's formation depend on knowing these elemental ratios. Is the surface rich in potassium, hinting at a volatile-rich origin? Could there be carbon patches suggesting a diamond layer deep below? No previous mission, not even MESSENGER, could map these elements globally. Now, with MIX calibrated and healthy, Mercury is about to reveal its true composition in X-rays for the first time. Mercury's surface is a cipher, its secrets locked in elements, gravity, and light. BepiColombo arrives with 6 questions that have stumped every mission before. First, why does Mercury's core claim nearly 85% of its radius, making it an outlier among rocky planets? Gravity mapping and radio science will measure the planet's mass distribution with new precision, searching for signs of ancient collisions or something even more unusual. Next, the puzzle of volatiles. Potassium, marked by its 3.31 kilo electron-volt X-ray line, persists on a crust scorched by the sun. MIXS will scan for this faint signature, testing whether Mercury formed rich in volatiles or lost them in a violent past. Theorists speculate about a diamond-rich layer beneath the crust, forged by immense pressure. X-ray fluorescence mapping will search for carbon's elusive trace. At the poles, ice endures in shadow, stable below 100 Kelvin, while equatorial temperatures soar past 420 degrees Celsius. Thermal imaging and hydrogen detection will probe whether these icy deposits arrived by comet or emerged from Mercury's own chemistry. Mercury's orbit, a proving ground for Einstein's general relativity, will be tracked with unmatched accuracy, hunting for the smallest deviation. Finally, elemental mapping will reveal if the crust is a patchwork of ancient remnants or a uniform shell. Each riddle stands, awaiting BepiColombo's verdict. Separation unfolds in seconds, but every move is the result of years of planning. At the edge of Mercury's gravity, the stack made up of MPO, MEO, and the Mercury transfer module awaits the signal. MEO spins up to 3 revolutions per minute, reaction wheels humming as sensors confirm the exact rate. Stability. Here is non-negotiable. Too slow and MEO could tumble. Too fast and its instruments face damage. The MPO, designed for 3-axis control, shifts to its own guidance, aligning for release. The transfer module's attitude control steps back, leaving the orbiters to steer themselves. In the control room, engineers track gyroscopes, star trackers, voltages, and every number matters. 8 pyrotechnic clamps hold the stack together. On command, all 8 fire in perfect sync, each bolt snapping free with a sharp jolt. The separation velocity is set at 0.4 meters per second, enough to clear the orbiters, not enough to send them off course. Too little force risks collision, too much and either orbiter could be lost. Within moments, MEO spins alone, antenna locked on Earth. MPO holds steady, preparing for Mercury orbit insertion. The transfer module, its mission complete, readies for a final burn, spiraling toward the Sun. Every step is logged, every scenario rehearsed. In the operations center, tension is thick. There are no second chances. 50 years ago, Mariner 10 raced past Mercury, sending back the first ghostly images of a world scorched and battered by the sun. The mission mapped less than half the surface and caught only hints of the magnetic field, leaving entire hemispheres and deep questions untouched. For decades, Mercury remained a planet glimpsed in fragments, a riddle at the edge of solar fire. Now, BepiColombo stands on the verge of changing that legacy forever. The gap between Mariner's fleeting flybys and the coming arrival of twin orbiters stretches across generations of science. Messenger filled in the map, but it orbited alone, unable to watch the surface and the magnetosphere in concert. No mission before has attempted what BepiColombo is about to do, deliver 2 fully equipped laboratories into orbit, working in tandem, each with a view the other cannot see. This is not just a technical upgrade, it is a leap from the era of snapshots to the era of full surveillance, a planetary autopsy with X-ray eyes and magnetic sensors. The timing is no accident. November 2026 will mark a half-century since Mariner 10's last pass. In that span, the tools of planetary science have evolved, but the questions have only grown sharper. Why does Mercury hide water ice in eternal shadow? How did it keep so much iron when the sun should have stripped it bare? The answers have waited through decades of speculation and model building, always just out of reach. BepiColombo is more than a spacecraft. It is the culmination of a 50-year pursuit, a relay passed from one generation of explorers to the next. The stakes are not only scientific, but cultural. When the data starts to flow, the story of Mercury will shift from myth to measurement, and the world that was once forbidden will finally become known. The moment is rare, a planetary secret poised on the edge of revelation. Right now, $2 billion and 8 years of risk ride the razor edge of Mercury's orbit, where solar wind is lethal and every answer triggers deeper questions. As BepiColombo closes in, the forbidden planet stands between us and the next leap in planetary science. What we uncover next isn't just about Mercury, it's about rewriting what we know of every world, including our own. Share your thoughts below.